Okay, welcome back. We're now about to see all the bad stuff that would happen to you if you fell into a black hole. All right, so this is the picture that's happening, but let's try to understand why this picture is happening. Lethal to humans, there's all sorts of good words on here we'll come back to in a minute. But let's go to our whiteboard and see why this happens. Okay, so let's imagine you've got a black hole down here. It's really small, it's a black hole. And you've got some object, I don't know, some person. Here's my stick figure person. And this person is obviously falling into the black hole. Now, this person, let me draw the black hole a little bit closer to the person. And you can see this a little bit better, right? All of the gravitational force is pointing directly towards this black hole. But you'll notice something interesting, like this person's foot is gonna feel a slight force in this direction as well as down. This person's foot, the right foot, is gonna feel a little bit pull both down and to the left. So you kind of get this squeeze effect where this whole thing seems to be squeezing a little bit. You also get a stretch effect because while it's no longer strictly true that F equals G m1 m2 over r squared, remember that was Newton's version of the force equation of gravity. This still works pretty well. And the closer you are to this object, the greater space will be curved and the greater force of gravity you will feel. The difference in gravity felt by this person's head and feet is going to be enormous. His feet is way more, feeling way higher gravity than his head is. And this is going to give you a stretching effect. These are kind of called tidal forces. And so the object will seem to get stretched, squished in this direction, and stretched in this direction. Tidal forces is really just the difference in force of gravity between one side of an object and another. And near a black hole, it becomes extremely large. So large that it would break you, in fact, apart. Okay, let's go back to our slideshow and think about this. The tidal force in the event horizon for solar mass blow would be lethal to humans. And that's an understatement, right? This is, imagine, the way I like to think about it is holding on to a overhead ceiling fan, right? The faster that ceiling fan goes, the more you get stretched. Well, this is a ceiling fan that you can't let go of, and it's going to suck you in. That's not sucking, but you're going to fall into it and get stretched and squeezed in this very, very intense way. Not only would it be lethal to humans, it's not just you can't survive this, it's the atoms in your body will physically get ripped apart from one another. Molecules will get ripped apart. Protons and neutrons inside atoms will probably get ripped apart. It's that strong a tidal force. And so, interestingly, if you do want to fall into a black hole and survive it, the larger a black hole is, the more massive it is, the gentler this effect is. The lower the tidal force, the weaker the tidal force is. So it's possible that if you had a supermassive black hole, one that were billions, millions, or billions of solar masses, and these things exist, then it's possible that you could actually survive the entry into a black hole without getting completely torn apart. Now, again, you'd never be able to tell anybody outside the event horizon what it was like, and you'd never be able to, and eventually you would get ripped apart because eventually you're just going to get towards the center of this thing, and you will get ripped apart eventually. But it's possible that you could see the inside of a black hole, at least for a little while, as you were falling through it. So that's fun. Okay, let's do a quick summary of falling into a black hole. The probe, so again, someone watching a probe fall in, that probe simply gets redder and slower, and the probe never appears to cross the event horizon. Time just gets slower and slower and slower, and you never actually see it cross. Now, if you were falling into the event horizon of a black hole, time always runs normally for you, no matter where you are, no matter what your reference frame is in. So you, falling through the event horizon of a black hole, don't notice anything unusual happening with time yourself. But as you're looking behind you, the universe gets faster and faster and faster. And in fact, as you cross the event horizon, you see the end of the universe. It ages to infinity behind you. If you want to know what the end of the universe is like, you just fall into a black hole. You will transport yourself by time-wise to the end of the universe. But of course, you won't last long enough anyway. You won't last very long anyway, because even if you choose a particularly large black hole, tidal forces will eventually lift you. Okay, so black holes. So questions. If no light can escape a black hole, and that was my certainly my assertion and is true, how can we see them? This is an interesting question because you may remember in the news a year ago, we had the first ever image of a black hole. In fact, almost exactly a year ago this week, the first ever images of a black hole were released. It was taken the year before that. So this is actually April 5th through 11th of 2018. The images were released finally in 2019. And this is what it looks like. Interestingly, there's a whole video about what we're looking at here. It's a fascinating thing, this little donut. It's phenomenal that they were able to do this. It's an unbelievable achievement of imaging and data processing and all of this stuff. The question is, what are we looking at? There's a video that I'm going to post. I'm not going to look at it here. I've posted it on the Canvas page where these videos will be posted. You can look at to see what this actually is. What you're looking at, sort of the middle here, is kind of the event horizon of the black hole. And this region is the area around it where there is stuff feeding into this black hole, accreting onto this black hole, falling into this black hole. And as the material falls near the black hole, it gets extraordinarily hot because of frictional forces. And those frictional forces are actually what's causing it to fall in as well. And probably causes an accretion disk. And you're seeing the accretion disk, although it's not really a top-down view of the accretion disk. There's all kinds of crazy stuff because, of course, near a black hole, the light's getting warped and bent all around and all sorts of crazy stuff. So take these images and look at this video because it's very cool. Anyway, we can, in fact, see images of black holes, at least the regions around them. This is another artist's conception of kind of the same thing for a type 1 supernova, right? You've got a very compact object here, another object that's spilling mass onto it. In this case, it's a black hole, though. What happens to this material as it falls onto a black hole? Well, probably it can't fall directly onto the black hole, but instead will fall into an accretion disk. This accretion disk will heat up from frictional forces and from other forces, and those frictional forces will cause it slowly to spiral in, but it will get very, very hot enough to emit X-rays. And so some binary systems actually appear to be emitting copious amounts of X-rays. Where are those coming from? Probably from some compact object like a neutron star or a black hole. Here's an example of one. One famous X-ray binary is Cygnus X1. Cygnus X1 meaning it's the brightest X-ray source in the constellation Cygnus. There it is. This is likely a black hole. How do we know it's a black hole? Well, it was discovered in the 70s. It flickers on a time scale of about a millisecond or a hundredth of a second. And again, if things are changing on this time scale, it limits the size to less than 3,000 kilometers. Its companion's a B7 supergiant, and we've measured the mass of this thing to be about 7 solar masses. The companion is about 30 solar masses, and the object itself the compact object is 7 solar masses. That can't be a neutron star. That has to be a black hole. And so there it is, a black hole, Cygnus X1. Okay, that's pretty much all I want to talk about today. We'll come back and wrap up a little bit next week on gravitational waves from black holes. I want to say one further thing about Einstein and Newton, though. Let's go back to the whiteboard. And I need to get up on my soapbox and talk about science for just a minute. So here is, remember, Newton's version of the force of gravity equation. Force of gravity, gm1 m2 over r squared. Einstein realized that this isn't really what's happening. It's really curved space-time. Does that mean that this is wrong? Does that mean that that Newton was futile in doing his experiment? In fact, the answer to that question is a resounding no, right? We use nothing more than this to take people to the moon. Unless you get into very specific regions of space-time, this equation works just fine for almost everything you could think about it. And this is a useful way to think about how science works in general, right? It's not that Einstein was right and Newton was wrong. It's that Newton's theory is limited to a box, right? This is Newton. Everything inside this box, meaning almost everything outside of black holes and light particles and things like that, Newton's theory works just fine for. Einstein just found the limits of that box and extended the box further out. In the limit of normal things, Einstein's theory is Newton's theory. Einstein's theory just makes the box a little bit bigger. We have not yet done an experiment that breaks Einstein's law, but there is probably an edge to Einstein's box that somebody will discover someday. An interesting region beyond which Einstein's theory doesn't even work anymore. And in fact, we have an inkling as to where that is already. We know that our current theory of gravity doesn't work very well with things like quantum mechanics at very small levels. And so we've never been able to see it in action, but it's probable that there is a boundary to Einstein's theory too. And that's the purpose of science. It's not to replace Newton or Einstein with something else. It's to realize find the edges of the box that Einstein's theory gives us and figure out a theory that gets us even beyond that. So that's my soapbox message for how science works. And it's the end of lecture for today. So enjoy your weekend. We'll come back next week and finish up our discussion of gravitational waves and black holes, and then get on to talking about the Milky Way galaxy. So enjoy.